Hello, welcome to this session on the design of brakes. The subject design of machine elements 2, subject code 18ME62 of VTU. So in the previous sessions, we have seen the design of band brakes, that is the simple band brakes and the differential band brakes. In this session, I will be explaining the design of block brakes. Block or shoe brake. This type of brake consists of a block or a shoe which may be rigidly mounted or pivoted to a lever as shown in the figure, and the braking is obtained by pressing this block against the rotating drum with the help of the effort F applied at one end of the lever. So the other end of the lever, as we can see from the figure, is pivoted on a fixed fulcrum which is denoted by O, and the distances on the lever, that is small a and small b, can be seen from the figure. That is from the center till the end of the lever it is A, denoted by A, whereas from the center till the fulcrum point O it is denoted by small b. Then we have the angle of contact of the block on the drum, that is denoted by 2 theta, and the frictional force produced by the block or the shoe on the drum or wheel will retard the rotation of the wheel. So the tangential force is denoted by F suffix T, whereas the reaction, that is the normal reaction, is denoted by Fn. So you can see the tangential force, it can be it is horizontal, may be moving to the left or it may be going towards right, and Fn will be acting vertically downwards. It is the reaction or the normal force on the shoe. So when the brake is applied, the lever with the block or shoe can be considered as a free body which is in equilibrium under the action of the following forces. First of all, the applied force or the effort, capital F, at the end of the lever. Then we have the normal reaction Fn between the shoe and the wheel, so that is shown here, it's vertically downwards. And then the frictional or tangential braking force Ft between the shoe and the wheel, that will be acting horizontally either to the left or to the or towards right. That is shown here. So for this configuration it will be acting towards right. And then since we have a fulcrum or hinge pin, so there will be a pin reaction. So these are the forces. So these are the terms which are used. F, capital F, is the required force or actuating force to be applied onto the lever. Mt is nothing but the torque on the drum. R is small r is the radius of the drum. 2 theta, you can see the angle of contact of that shoe or block, and is not F, it should be mu. Mu is the coefficient of friction, and Ft is the tangential force, which we know that it is given by the ratio of torque to the radius, and Fn, because of pressing of this shoe there will be a normal force Fn, and we have A, B and C, which are the distances. A is the distance between the center of the shoe and the applied force, B is the distance between the fulcrum and the center of the shoe, and C is the distance between the fulcrum and the line of action of the tangential force F. So we will consider the following three cases. So first case, when the tangential force Ft, the line of action of this tangential force passes through the fulcrum pin. Okay, this is the first case. That means the fulcrum is placed in such a way that its position is in such a way that the tangential force will exactly pass through that point or the center of the fulcrum. That means, so here first case, if the drum is rotating in the clockwise direction, then so what happens? Then, as I said earlier, the Ft actually depends upon the rotation of the drum, whether clockwise or counterclockwise. So when the drum is rotating in the clockwise, means the Ft, according to this diagram, it should be acting towards the fulcrum. Suppose if the drum is rotating in counterclockwise direction, then Ft will be acting away from the fulcrum. So taking the moments about the fulcrum point O, so the effort F into A plus B is the distance from on the lever, that should be equal to, that is the anti-clockwise moment, should be equal to Fn into B, that is the clockwise moment. So now we know that Fn can be written as Ft by mu, since Ft is nothing but mu into Fn. Okay, so we can write Fn as Ft over mu. So if we substitute that, we will get the effort F as Ftb divided by mu into A plus B, or we can write this further as, simplify this according to the equation given in the data handbook 13.17a as Ft b by A plus B into 1 by mu. So this is the expression for the effort for this particular case when drum is rotating in the clockwise. Suppose the drum is rotating in counterclockwise direction, then as I said earlier, so Ft should be acting away from the fulcrum. Ft will be acting away from the fulcrum. So similarly, taking moments like we did in the last case, here F into A plus B, that is the anti-clockwise moment, is equal to Fn into B. Again substituting the same thing, so we get the same equation, F is equal to Ft into B by A plus B into 1 by mu. So why I have written the same thing for clockwise and counterclockwise rotations is that the actuating force remains the same for both Ft towards or away from the fulcrum, or in other words, for both clockwise and counterclockwise rotation of the drum. The effort F required is the same for this particular case, that is the first case where the tangential force Ft is passing through the center of the fulcrum. Now case 2. Case 2 is nothing but whenever the line of action of the tangential force Ft is in between the fulcrum and the center of the drum. That means the fulcrum is somewhere at some distance c, the distance between the fulcrum and the tangential force Ft is denoted by c in this diagram, as you can see. So therefore Ft is now in between the fulcrum and the center of the drum. Now taking again moments about the fulcrum point O, we find the force effort F into A plus B plus Ft into C, that is nothing but the clockwise moment, anti-clockwise moment, sorry. So that is equal to Fn into B, but we know that Fn is equal to Ft by mu, or Ft is equal to mu into Fn. So therefore substituting that, we get F into A plus B is equal to Ft B by mu minus Ftc. So that will give you Ft into, taking Ft outside, B by mu minus C. So again taking B outside, we get Ft B into 1 by mu minus C by B. So this gives the effort as F is equal to Ft B by A plus B into 1 by mu minus C by B. Next, coming to the counterclockwise rotation of the drum. For the counterclockwise rotation, we find that the Ft is moving away from the fulcrum. So taking moments about the fulcrum point O, as we did in the last case, F into A plus B is equal to Fn, normal force, into B plus Ft into C, where Ft is the tangential force and C is the distance till the fulcrum. And we know that Ft can be expressed in terms of the normal force as mu into Fn, or Fn is equal to Ft by mu. Substituting the same thing over here and taking Ft outside, we find the expression Ft into B by mu plus C. So taking again B outside, we get Ft B into 1 by mu plus C by B. So finally we get the expression F is equal to Ft B by A plus B into 1 by mu plus C by B, given by equation number 13.17c, design data and book. Now coming to case 3, where now the fulcrum is in between the tangential force Ft, the line of action of the tangential force Ft, and the center of the drum. So here again, considering the two directions, clockwise rotation and counterclockwise rotation. First, for the clockwise rotation of the drum, again taking moments about the fulcrum point O, so F into A plus B can be given by Fn into B plus Ft into C. Again, C is the distance between the fulcrum and the tangential force Ft. So if we substitute for Fn as Ft by mu and simplify this, finally, like we did in the last case, we get the expression F is equal to Ft B by A plus B into 1 by mu plus C by B. This is given by the equation number 13.17d. Now for the third case, if we consider the counterclockwise rotation of the drum. So what happens? For clockwise rotation of the drum, Ft was moving towards the fulcrum. Now for counterclockwise rotation of the drum, Ft is moving away from the fulcrum. So again, taking the moments, we find F into A plus B plus Ft into C, because Ft is now moving away from the fulcrum. So therefore the moment becomes counterclockwise.
So again is equal to Fn into B. So again substituting for Fn is equal to Ft by mu and simplifying, we get the expression F is equal to Ft V by A plus B into 1 by mu minus C by B. This is given by. So in this slide you can see the three cases together as given in the design data handbook. The first case, the tangential force passing through the fulcrum point O, and for both clockwise as well as counterclockwise we have the same formula, F is equal to Ft into B by A plus B into 1 by mu, given by 13.17a. And for the second case, that is the Ft will be in between the fulcrum and the center of the drum. So for clockwise rotation we have Ft B by A plus B into 1 by mu minus C by B, the effort. And for counterclockwise direction we have Ft B by A plus B into 1 by mu plus C by B, given by 13.17 B and C. And for the third case, that is fulcrum will be in between the tangential force Ft and the center of the drum. So we find for clockwise rotation F is given by Ft B by A plus B into 1 by mu plus C by B, and for counterclockwise rotation F is given by Ft B by A plus B into 1 by mu minus C by B, given by the equation number 13.17D and 13.17E. So when the angle of contact between the shoe or the block and the wheel is less than 60 degree, then generally we assume that the pressure or the normal pressure between the shoe or the block and the drum is uniform. But when the angle of contact becomes more than 2 theta, becomes more than 60 degree, so we assume that the unit pressure that is normal to the surface of contact between the shoe and the drum is lesser at the ends than at the center, and the wear in the direction of the applied force is uniform. So in such a case we have to use equivalent coefficient of friction mu dash in case the angle of contact becomes greater than 60 degrees. So that in that case equivalent coefficient of friction mu dash is given by mu into 4 sin theta by 2 theta plus sin 2 theta. So where mu is the actual coefficient of friction and 2 theta is the included angle and theta is the semi angle of the block. So the brake is said to be self energizing whenever the frictional force or the friction helps to apply the brake. The friction between the block and the drum helps to apply the brake, and if this effect is great enough to apply the brake with zero force, that means no force is required to apply the brake, the braking action is obtained by itself, then it is called self-locking. So the brake is said to be self-locking when the applied force F is 0 or negative. And in case of this shoe brake, the normal pressure of the shoe on the block onto the drum is given by the normal load or the normal force Fn by the projected area of the shoe. So this projected area is given by 2 b dash r sin theta. If we find out the projected area of the shoe, it becomes 2 b dash r sin theta. Just you can remember this, where b dash is the width of the shoe. Okay.